these couple of studies are very much focused on California, but the message is good and some of the lessons can be learned and applied anywhere in US and also maybe in India at some point. It looks at these two studies look at basically how the growth of EVs in California and their demand for electricity for charging the cars is affecting the rates, utility rates for everybody, and how this may require some reorganization of the grids at some point, which is obviously a good thing to look at because we are pushing EVs very hard as climate solutions, and of course the energy to charge them has to be clean as well, which is not the case all across the world. And also they need a charging station infrastructure, and the grids have to worry about how to deal with the charging. So let's just look at some of the messages from these two studies. I'll just read the some of the summary from the first paper, which is here. It's an NRDC report. The rate structure that a customer is on impacts both the utility revenues associated with the EVs and EV charging behavior. So we'll see what that means. And secondly, the associated electric supply and distribution costs are also affected in terms of the rate structure from UV charging. Importantly, we find that EVs generate more utility revenue than costs and put downward pressure on rates for customers in both cases. Okay, so just in terms of the numbers from California, a number of vehicles in thousands that are using various utility companies, PG&E, SCE, SDG, and E. These are three different power suppliers, electricity suppliers in California, in the utility service territories, as you see. So obviously the numbers have grown quite significantly for these two and not so fast but growing for this one. I won't go into the differences. There must be some issues involved in choosing one or the other. Looking at the percentage of whole home energy consumption during off-peak hours. So the first idea is to see if the rate of electricity you draw depends on time of use. At peak hour you pay more, off-peak hours you pay less. Then as a EV owner, are you going to charge in the peak hour or the off-peak hour, and how that affects the revenue for the company? For example, a lot of charging on off-peak hour obviously would consume more electricity at a lower rate, but how does it affect the overall revenues and affect the utility rates for all? Okay, hold on a second, I'm getting a call here. Sorry about that. So the ideas are simple, just to look at California, and we have discussed the California effect elsewhere, how California does something very progressive like carbon tax or carbon trading, or figuring out cost of EVs on general utility rates and so on, and then other states tend to follow it, but obviously it can also go beyond when the solutions are good. So this is just few numbers from California. Percentage of whole home energy consumption during off-peak hours. So these are two utility companies again. Off-peak usage for EV time of use rate and non-EV residential. So non-EV residential is still higher, but you can expect these to grow rapidly, and on this it's similar but smaller as we saw before. The share of charging occurring during on-peak and other hours, looking at again different utility companies, and on-peak and all other hours. Most of the charging happens during all other hours and not on-peak hours. Basically people are being intelligent about paying as little as possible and using energy on peak hours only when absolutely necessary, or it could be these are only households, so obviously we are not talking about industries and businesses. Revenues and costs of EV charging for 2012 to 2021 in millions of dollars pegged to 2021. So here are the revenues and costs. So they go for energy, capacity, transmission, distribution, and EV programs, and for each utility company it's similar. So EV programs are adding revenues in terms of paying for electricity for charging, but they are also adding costs to the EV charging stations, etc. I suspect you can look that up. From the second paper from IEEE, we look at a graph showing the number of EVs added per feeder. This is in the grid sense, so there's a utility company and there's a grid that is feeding energy to the network. As a function of the feeder's peak demand, each feeder is represented by a blue dot. The dashed line, red line, indicates y equal x. So you can see that number of EVs are not really highly correlated with the feeder peak demand in kilowatt hours. So that's a good point. And this paper looks more at how the grid itself has to consider the growing number of EVs wanting to charge and the charging station network that are going to be built, which Tesla has already done across many hotels and so on, for example, in the US, not just in California. The power demand, looking again at a particular day, the diurnal cycle. So the EV load profile at residential locations for 100 EVs for low demand. This paper involves some modeling for designing optimal grids, feeders, and so on, which I'm not going to get into. Middle demand and high demand scenarios. So these are scenarios which are modeled. So you can see when the peak happens. So demand goes up, but the peak doesn't shift significantly. It is still in the evening and night hours going in here, and not during the morning and daytime hours, which are typically the peak hours. This is the feeder power demand in megawatts for another day. The historical load shape from SCADA measurements and load shape with additional EVs and PVs. So this is historic data from 2016. So before EVs, what you had, and after EVs, how the feeder power demand went up. So this talks more about how the grids need to consider this growing demand that's going to come in. And so there are two issues: how to deal with the EV charging demand in terms of grids and distributed energy sources feeding into the grid and such. And the other one is how EV charging is going to affect the overall revenues for the utility companies, and how that's going to affect the rates. So in countries like India, where large parts of the electricity is still owned by the government, more and more private players are in the game, of course, for a while, like Tatas, Adanis, Ambanis, and so on. So this is going to become important for India, as well as India keeps pushing EVs as a part of its nationally determined contributions, and to improve its own air quality and reduce health impacts and so on. So EV load demand in kilowatts, again, an example of the spatial distribution of the EV load demand at the peak time for a feeder. The load demand is summed over intervals of half a kilometer, so how far you are. So this again goes into calculating the feeder requirements that I won't go into, but just to conclude this podcast, let's read what the paper concludes. As the spread of solar PVs and fast charging EVs make power systems less predictable, so putting a charging demand versus intermittency of the solar PVs are generally going to make the power systems less predictable in terms of the demands. Forms of dynamic pricing have been suggested to align real-time distribution grid conditions with economic incentives. So having a lower off-peak rate, time of use based rate, is going to obviously smooth out these spikes and dispatchability required, which is not met by solar and wind, for example. While some control strategies and business models exist at the transmission grid level, distribution grids are in the very early stages of adopting dynamic pricing. The path forward for high EV penetration includes a combination of innovations in time of use rate designs, long-term load forecasting to plan grid reinforcement, and distributed energy resource management system where wind and solar are feeding into the grid, and people are maybe even giving back to the grid when the EV is parked and the battery is just sitting there, and so on and so forth. So DER management system with a local dynamic price signals to optimize the grid for EVs and DERs are going to be part of the path forward for for high EV penetration into the market, which is what you want. Already, I think 1 out of every 8 cars bought is a EV across the world, but the investments in internal combustion engines is still there. They are not going to be phased out anytime soon. Plus, there are going to be large transport trucks and so on, which are not going to be easily electrified as quickly as the small passenger cars or scooters and bicycles and so on, for example. Okay, so that's just a short message, but I thought it's important to see that along with the solutions in terms of EVs, we have to also worry about what EVs. If you are an EV owner, let's say you are richer than somebody who doesn't own an EV, but you are sharing the utility and the rates are going to be affecting everybody. So you have to worry about how EV charging will affect the rates for everybody, and you have to worry about how the grid itself has to be designed and with charging stations to meet the demand from growing number of EVs, okay? Especially with the dispatchability issues of solar and wind, because you want the EVs to be charged with clean energy in the end, right? So let's leave it here.